It's Daddy Cause, and in this video we'll be looking at the electromotive force of an electrochemical cell. To start with, to start with, I discussed with you that electrochemical cell involve two half cells connected together, and that when you connect the two half cells together, the electrode or the metal that is higher in the activity series will serve as the anode, which should be the one that will produce the electron that will go to the cathode. Cathode is the receiver of the electron in this case. And as you can see, the element X here has been labeled the anode. So we can assume that X is higher than Y in the activity series if it's the anode. So electron will have to flow from the anode to the cathode. So that's the flow of electron. So don't forget that current flows in opposite direction to electron. So that when electron is flowing from anode to cathode, then current will flow in the opposite direction. That's from cathode to anode. So here now, you will see that the anode will dissolve and produce electron that will travel through the wire to the cathode. And remember that the salt bridge also will allow movement of ions between the two solutions so as to prevent charge separation that will stop the reaction from continuing. Now let's look at what electromotive force is. The electromotive force is the potential difference that is responsible for the flow of current from an electrode of higher potential to an electrode of lower potential. Electron flows from the anode to cathode, but current flows in opposite direction from cathode to anode. Now do not forget that the cathode will always have higher higher electropotential. That is, it will be maybe more positive than the anode. So the more positive the electrode, the more tendency it has to become a cathode. So if we have two electrodes, the one with more electrode potential, which is coiled from the word reduction potential, that one will serve as a cathode. The one with smaller electrode potential, the one with like a more negative electrode potential, that one will serve as the anode. That one is always higher than the one that is having more reduction potential in the electrochemical series. So when current is flowing, it flows from cathode to anode, but electron flows from anode to cathode. Don't forget, electron flows in opposite direction to the current, and you have been well aware that electron will move from anode, which is the higher metal in the activity series, to the cathode, which is the lower metal in the activity series. The higher metal in the activity series always have smaller reduction potential. The lower metal in the activity series always have bigger reduction potential. So take note of that. So in our definition, we are saying that the potential difference that is responsible for the flow of current, or if you like, the flow of electron, the potential difference, the force that is responsible for the flow of electron, or if you like, the flow of current from the electrode of higher potential, that's from the cathode, to the one of lower potential, that's from the anode. So if you are talking about flow of current, current will flow from cathode, that's one with higher potential, to anode, the one with lower potential. But if you want to use flow of electron flows from anode, that's the one with lower reduction potential, and flow to cathode, that's the one with higher reduction potential. So whichever way you put it, ensure that your definition is correct. The potential difference responsible for flow of current from cathode to anode, or if you like, the potential difference that is responsible for flow of electron from anode to cathode. Take note of that. That is what is called the electromotive force of that cell. And there are three factors that affect the value of the EMF. Number one, the nature of the electrode that was used. Now, let me tell you the meaning of that. If X and Y are close, their position are closed in the electrochemical series, the EMF will be small. So if you want the electron or the current to be moving very high and very fast, you want the EMF to be large, then try to use two elements the electrode potential is very far, or whose position is very far from each other in the electrochemical series. If you use two metals with, you know, very close position, the EMF will be small. But if you use two metals with very far apart position in the electrochemical series, then you are going to have a very large electromotive force. That is a very large potential difference between two of them. That's number one, the nature of the electrode that you use. Number two, the temperature affects the value of electromotive force. I've explained that under under electropotential. Then concentration also affects the value of electromotive force, including pressure, if gases are involved in the reaction. So take note of that. If you want to get a very big EMF, use two metals whose position are very far in the electrochemical series. The formula for EMF is E cathode minus E anode. That is the electropotential of the cathode minus electropotential of the anode. So the cathode, don't forget, is always the lower metal in the activity series, or if you like, the one with higher reduction potential. The anode is always the higher metal in the activity series, or the one with lower reduction potential. Take note of that. So the formula for EMF is E cathode minus E anode. Some textbook will tell you that it is E reduction minus E oxidation. No problem, because reduction occurs at the cathode, whereas oxidation occurs at the anode. However, to avoid any confusion, just stick to E cathode minus E anode, because you are able to know which of the half cell will be the cathode, which of the half cell will be the anode, based on their position to each other in electrochemical series, or based on their reduction potential in the question you'll be given. So the formula for EMF is E cathode minus E anode. Let's look at example 1. So we are given an electrochemical cell constructed from two half cells. So the first half cell is the copper half cell, which is written as Cu 2 plus Cu plus 2 electron give us Cu, and the reduction potential of the copper half cell was taken to be plus 0.34 volts. Whereas the one for zinc, the second half cell, is given to us as Zn2 plus 2e minus, giving us Zn solid, and the reduction potential was minus 0.1 volt. That is, those are the two values we are given for the reduction potential. Now you will see that the value represent reduction potential, because if you look at the two equations, they are reduction equation. So you can see that your electron is on the right side whenever, or on the left side. Whenever your electron is at the right hand side, is a reduction half equation. So that's why you know that these values are reduction potential. Reduction potential. So, and I taught you before this page that the one with higher reduction potential is the cathode. As you can see that copper is having higher reduction potential plus 0.34, so it's going to be the cathode. Or if you consider their position also, copper is lower than zinc in the activity series, so copper will still be the cathode. So take note of that. So we have to answer the following 7 questions. Number one was to construct a diagram for the electrochemical cell. Construct diagram, so that means you are going to have the two half cells joined together. Then we have to show direction of the electron flow. Then from there calculate the EMF. Then write half equation for the two reactions occurring at the cathode and anode. Then calculate the overall write the overall equation. Calculate the delta G and write the cell notation of the cell. So we look at this question one after the other and see how we solve them. So the first thing is to uh, write the diagram of the electrochemical cell. Now don't forget that we have two cells in this place. We have the uh, copper half cell and we have the zinc half cell. So let's move. The copper half cell, that's a beaker, right, containing Cu2 plus. Then inside it you dip a copper metal. Don't forget, that is half cell. That's copper half cell. Also we have zinc half cell. You can represent copper half cell. You can represent the copper half cell by this notation: Cu2 plus slash Cu. That's copper half cell. Now let's do for zinc half cell. That's zinc ion. Then inside it you dip a zinc metal. So this is zinc half cell. Talk about Zn2 plus slash Zn. So that's the zinc half cell. So to get our to get our electrochemical cell, you connect the two of them through wire. You can put a voltmeter there, right? Then you join them by short bridge. Let me use a blue one for short bridge. Can you see that? So you know what a short bridge is. So that's the structure of the electrochemical cell. You label this as your short bridge. That's your short bridge. Good. That's a short bridge. Now, between copper cell and zinc cell, which one will be our cathode? Which one will be our anode? So here in this place we know that copper will be our cathode because it's lower than zinc in the electrochemical series. So copper becomes our cathode. Cathode is positive in electrochemical cell. Then zinc will be our anode. This is our anode. The anode is negative in electrochemical cell. Don't forget that. Alright, so we are done with the first question. This is how to construct the diagram of the electrochemical cell. Just get the two half cell, join them by a wire. You can put a voltmeter to show that there's a reading going on. Then next, put the short bridge to allow flow of ion. So that's all. So the next thing is now to do the direction of electron flow. Now we know that the electron will always flow from the anode to the cathode. Current will flow in opposite direction, but here we ask for direction of electron flow. So just use an arrow to represent. Let me use a red arrow in this case. So just put arrow there and put the electron. Put arrow there and put the electron, or if you like, you can put it on the wire. Electron. So anyone, though I always prefer that you use arrow and put electrons. So that's the direction of electron flow from anode to the cathode. All the time, electron will flow from anode and flow to the cathode. Take note of that. So we have answered question A and B. We have drawn the cell, and then we have also shown the direction of electron flow. So let's move to question C. Question C is asking us to calculate the EMF of the cell. The EMF of the cell. Now don't forget that the EMF is always EMF, or if you like E naught cell. Anyhow you can call it E naught cell. Standard electromotive force of the cell. E naught cell is E cathode minus E anode. Don't forget that. E cathode minus E anode. So what's that giving to us? Our cathode is copper because it has the higher reduction potential, or if you like, because it's lower than zinc. So our cathode is copper, that is 0.34. You can put the sign plus 0.34. Our anode is minus 0.71. So minus 0.71. So what would that give to us? That will give us 0.34 plus 0.71. So that will now give us 1.05 voltage. Now you have to put the sign there. The sign is positive. This 5, this 10, that's 0. So that will be 1.05 voltage. So that will be the answer of the EMF plus. Or put the plus and put the voltage. That is when you can get mark. The plus is not a mathematical sign. The plus is a chemical sign. So take note of that. So it's very important. So the E naught cell, the EMF of the cell is plus 1.05 voltage. So now you can write under the cell that your EMF is plus, your EMF is plus 1.05 voltage. So let's answer the next question, question D. So in question D, we have to write the half equation at each electrode. Now this is where we need to be very, very careful to write half equation. Now we know that the cathode is a site of reduction. So what happens at the cathode is reduction. And if you look at these two equations, you will see that they were given to us as reduction equation. Both of them are reduction potential. See, Cu2 plus 2e, that's reduction. Electrons at the is at whenever your electron is at the reactant side, it's a reduction process. Can you see also this one also is also reduction? So they are given to us as reduction. But we know that in the two half cell, only one of them is reduction, the other is oxidation. So every time your cathode will be left as reduction, whereby your anode is oxidation. So it will be switched, it will be interchanged. So what do I mean? Look at it. So I will write for my cathode side. For my cathode, I'll be having Cu2 plus 2e minus give us Cu solid. That's for the cathode. Just repeat the equation like that for the cathode. However, for the anode, because we know that what happens at the anode is not reduction. Anode is a site of oxidation. So what we just need to do is to reverse the equation. You know what we have for zinc anode presently now is reduction. So just change the position of the product and reactant. You get back an oxidation process. So this zinc that is at the reactant side, take it to this zinc at the product side, take it to reactant side. This zinc at the reactant side, take it to product side, then you see that the equation will become an oxidation equation, because that is what always happens at the anode. So now you're going to have zinc, that's from the product side now, giving us what? Zinc 2 plus, zinc 2 plus 2 electron. That is the equation at the anode. So take note of that. Just repeat the equation for cathode, but reverse the equation for anode. That's all. To now write the overall equation, you know already how to write overall equation. Check for the electrons, make them equal if they are not already equal. But in this case now, the electrons are equal. 2 electrons here, 2 electrons here. If the electrons are not equal, then you make them equal by multiplying one of the equation of the two equations by an integer that will make two of them to be equal. But in this case, we don't have problem with electrons. They are both equal. So when electrons are equal, what do? You cancel them out. So now we have cancelled the electron out. We now want to write our overall equation. Now take note, this electron that we cancelled out is called number of electrons transferred in to calculate the spontaneity or to determine the spontaneity, that is workability of a cell. You need that number, the number of electrons that was transferred. In this case, it was 2 electrons. So that is the number of electrons that you cancel out. That is the number of electrons that was transferred. So take note of that. We need the value later. So let's write our overall equation for that reaction. So what do we have? At the reactant side, we have Cu2 plus aqueous plus Zn solid, giving us what? Cu solid plus Zn2 plus aqueous. That's our overall equation. The copper here is aqueous, the zinc here is solid, the copper here is solid, the zinc here is aqueous. So that is how we get our overall equation. Very simple, isn't it? So that's how we do it. So the next question we have is question F. Question F asks us to calculate the delta G for the reaction. Delta G actually means Gibbs free energy change. That delta means change. So change in free energy. So the free energy is energy available to do work. That's the meaning of delta G. That's the meaning of G. So delta G represents Gibbs, that's change in Gibbs free energy. Change in, that G stands for Gibbs free energy. Gibbs free energy. So it's always used to determine whether a reaction will be spontaneous or not spontaneous. Spontaneous means whether a reaction will occur on its own or it will require an external help. That's the major usefulness of delta G. And whenever your delta G is positive, the interpretation is that the reaction is not spontaneous. The reaction will not occur on its own. Non-spontaneous, non-visible, non-spontaneous when it's positive. But if your delta G is negative, it means the reaction is spontaneous. That is, the reaction will occur on its own. It's spontaneous. It's spontaneous. Now, the delta G can be 0. That means the reaction is at equilibrium. So those are the 3 possible values you can get from delta G, and that is their interpretation. Whenever your delta G is positive, that battery cannot work. The battery will not function. But if it's negative, kudos, it's going to work. So take note of that. Now let's go to the question proper. Calculating of delta G as formula, and the formula is delta G, that's the connection between delta G now and EMF. Delta G is minus NF E naught cell. The E naught is standing for the electromotive force of the cell. So already delta G, you know the meaning is change in Gibbs free energy. N that I was telling you before is the number of electron transferred. Number of electron transferred. That's the number of electron that cancels out. That's delta G. Take note of that. Your F is constant, is Faraday's constant, 96,500 coulomb. That is your F, is always constant. In fact, sometimes you'll be given the value of F in your question. Is always constant at 96,500 coulomb. Then your E stands for the EMF of the cell. EMF of the cell. Take note of that. EMF of the cell. So for this question now, what is the EMF of this particular, what's the delta G value of this cell? Delta G is minus 96,500 coulomb, right? Times, sorry, not 95, minus 2 times, 2 is the number of electrons that was transferred. That's what our N represents. Then F is the Faraday's constant, 96,500 coulomb. Then E stands for the electromotive force of the cell. In this case, our E was 1.05. Don't forget, 1.05. That is what our E was, 1.05. So that's how you write it. Very simple. Next, calculate your answer. So delta G will now give you 96,500 times 2 times 1.05. That gives us 202. That's plus, sorry, not plus, minus 202,650 joules. The unit of delta G is joules. You must put joule. You must put the unit. And then you must also put the sign, because the sign of the EMF is very important. If the EMF has been negative, for example, it will have affected the minus here and give us a positive delta G. And once you have the positive delta G, that means the reaction is not going to work. So that's why EMF can be used to determine the spontaneity of a reaction, because it is related to delta G, which determines whether a reaction will be possible or not possible. So put the sign and put the unit of the delta G. If you want to find it in kilojoule, just divide by 1,000. If you divide by 1,000, that will give you minus 202.7 kilojoule. So any of the two, you'll be fine. So thank you. That's how you do delta G. Then finally, we want to write the cell notation. Cell notation, or line notation. Instead of writing all the long equation that we did for overall reaction of the cell, you can just shorten it. We call that short form, the line notation or the cell notation. Now, when you are writing cell notation, the formula that you're going to use is this. is very easy. The formula is anode material. Let me write for you here. The formula is anode material slash anode solution. So I think my handwriting is very big here. Let me reduce it. So anode material slash anode solution double slash cathode solution double slash cathode solution single slash cathode material. So that's the formula that you are going to use to write out your line equation. Very, very easy. In the case of this question that we are doing, the anode material is zinc. Zinc is the anode material, zinc metal. The solution of the anode is zinc ion. That is the solution inside the ion inside the solution of the anode is zinc ion. Then here our cathode solution is a copper ion, Cu2 plus is inside our cathode solution. Then what is the material that the cathode is made of? That is copper cathode. So that's copper metal. So that is the formula, very easy. Now, what is the meaning of slash? A single slash represents phase difference, because you can be asked in exam, what does that single slash represent? It represents the phase difference, that is change in physical state. That's the meaning of phase difference. We are moving from a solid metal to a solution. That's phase difference. Whereas you can guess what is the double slash representing? Is representing the salt bridge. Is representing the salt bridge. That is the meaning of both single slash and double slash. So double slash represents salt bridge, single represents the phase difference. And now let's come and use this particular formula to write out our answer. Don't forget, our formula is supposed to go like anode material slash anode solution double slash cathode material slash cathode solution. So what is our anode material in this place? That's zinc. That's the metal of the anode. That is zinc, right? Zn solid. What is our anode solution? That's zinc ion, Zn 2 plus aqueous. Then double slash. So we are done with anode. This side is the anode side. So we are done with the anode side. Then double slash means salt bridge. Now we are going to the cathode. At the cathode material first, which is Cu 2 plus aqueous single slash cathode solution, which is no, it's not cathode material. It's cathode solution first before cathode material. Please, that's supposed to be an omission or an error there. So that's cathode solution first, Cu2 plus aqueous single slash Cu solid. That's our cathode material. So take note of the formula: anode material slash anode solution, then followed by cathode solution single slash cathode material. That's the formula for every line notation that you want to write. start with the material of the anode, single slash, the solution of the anode, double slash, solution of the cathode, single slash, the cathode material. Take note of that. So this is the line formula for that particular cell. Very easy. Put the physical state, put the ions where appropriate. So that's the line notation of the cell. So everything about the cell is displayed here. Everything about the cell is here. So this is the diagram of the cell, right? The cathode is copper because it's lower than zinc. This is the salt bridge that allows movement of electron, movement of ions between two cells. This is the wire that allows movement of electron. Then this is the direction of electron flow, as you can see here, moving from zinc to copper. Moving from zinc to copper, because zinc is higher than copper in the activity series, or zinc has lower reduction potential than copper. Take note of that. Then this is the equation at the copper electrode. That's reduction because it's cathode. This is the equation at the zinc electrode. That's oxidation because it is the anode. Then this is the line notation. This is the line notation. That's the line notation, which is anode material, single slash, that's for phase difference, anode solution, double slash, that's for salt bridge, cathode solution, single slash, cathode material. So take note of that. That's how you write your line notation. So this is the full description of this particular electrochemical cell. So now let's look at some things you are supposed to do, and this will be our exercise 2. I've given you one before in the previous video. So look at this particular question. Construct state diagram, write arrow to show direction of electron flow, find EMF, write half equation at anode and cathode, write overall equation, calculate delta G, and write the cell notation for the cell. Then for the next one, you also do that. Now the difference between exercise 2 is that there are 2 ways you can determine your anode and cathode. You can use either the electropotential, or you can use the position of the 2 metals in the electrochemical series. The higher will be the anode, the lower metal will be the cathode. Or if you are using the electropotential, the higher, the more the electropotential, then that one will be the cathode. The one that has lower electrode potential, that one will be the anode. So take note of that. But here in exercise 3, you are only giving X and Y. So there's no X and there's no Y in the electrochemical series. So the only way you can know which one will be the anode or the cathode is the electropotential. So don't forget, it's sufficient enough to let you know your anode and cathode. The one with more electropotential, that one is going to be cathode. The one with less electropotential, that one will be anode. Take the minus into consideration. -1 is bigger than -3. Take note of that. So you write your cell equation, you write your cell diagram, you show direction of electron flow, and find answers to the other questions that you are being asked to do in this place. So do it in your notes, and I come along with it as exercise or assignment. So that is how you will do this exercise 3. And don't forget also that your electron will flow from the anode and flow to the cathode. It's very, very important. So take note of that. So I will be talking about primary and secondary cell in the next video. God bless you.